Hello, this is the second part of 4.2. We already did Rolle's theorem, and Rolle's theorem was where as long as my function was differentiable and continuous over an interval and the y values were the same, there had to be some place where f prime of c, so that c is in between the endpoints, had to equal 0. So let's look at something very similar to that called the mean value theorem. So we are going to draw a function, okay? And my function here is going to have, so I need to have a function here. There's my function. It's continuous, it's differentiable. I don't have any holes, I don't have any corners, jumps, that kind of stuff. And I need to have two places that have different y values. So if I have this place right here where I'm using this y value, and maybe this one down here where I have like that y value, I can find places on my graph where some things happen. Alrighty, so last time we were together, we made sure that the y values were the same, and we said, well, in between those two endpoints, which we called A and we called B, again, as long as it's differentiable over that interval and continuous over the closed interval, there had to be at least one place in between where the derivative or the slope value of the tangent line had to be 0. And what's changed here is instead of it being 0, I now am looking for a place where the point where the tangent line, which the slope of the tangent line, which happens to be the value of the derivative on that curve, is the same as the slope of the secant between those 2 points. So again, let's look at a more formal way of the mean value theorem here. So take a minute and write this down. So mean value theorem, again, is a lot like Rolle's theorem. It must be continuous over the closed interval. It must be differentiable over the closed interval, but I do not have to have y values are the same. But I do know that once I find those y values, that the slope of the secant must equal the slope or the derivative value somewhere in between that curve. Alrighty? Or we can rewrite it as, hey, look at that tangent line right there. That's my equation of my tangent line, and I am solving for the slope is what I'm doing, finding where that slope occurs. So looking at this, again, slightly different than Rolle's theorem, if I look at this first one and I notice that the function is continuous, so we'll call it f, is continuous from some a to some b. I know that f is, oops, that has to be closed interval. F is differentiable from some a to some b. Then there is at least one place where f prime of c is equal to the slope of that secant line, and that slope of that secant line is going to be f of b minus f of a over b minus a. Okay, so I can look at another example here, and I am just going to pick random spots where my y values are not equal to each other. So I'm going to pick a spot here, and I'm going to call this sum a. And I'm going to pick a spot right here, and I'm going to call that sum b. And again, if I create this secant line in between there has to be at least one place in between a and b. This is being my a, this is my b, where the slope of the tangent line is equal to the slope of that secant. And I can see from my drawing here, if I try to replicate that, looks like this might be some c value. And again, as I try to find that, it might be right about here. And so that might be my other c value. Okay. So we're going to start with the same kind of thing we did with Rolle's theorem. And we are going to start by drawing the mean value theorem here. So the first thing I'm going to do is I am going to start with finding that secant line. So I'm going to draw the secant line between my two endpoints. And I am going to try to find, based on that secant line, any c values where the derivative, or the slope of the tangent, is exactly equal to the slope of the secant. See if you can do that right now. So doing the best kind of drawing that I can do, I seem to have 3 places where that occurs. So again, on number 12, I'm just going to call it number 12. And number 12, I have to tell you that f of x is continuous through the interval. It's going from 1 to 14. From 1 to 14. I must tell you that f of x is differentiable from 1 to 14. And I know it's continuous because there are no holes, no jumps, no other discontinuities. I know that it is differentiable because it is a smooth curve, again, without any holes or jumps, corners, cusps, that kind of thing. And if that is true, then there must be at least one point along here, at least one c value, where the derivative at that c value, or the slope of the tangent line at that c value, is equal to the slope from 14 to 1. Okay, and to me, when I look at that, it looks like it's occurring at, let's see, c would be 3. It looks like it's occurring at c equals 9, and it looks like it's occurring at c equals 13. Okay, so let's do our problems just like we did last time. I am going to go ahead and work on these problems. Why don't you work on them with me? Well, let's store that over here on the side, and let's start working on a couple of these questions. So let's start with number 13. Number 13, I have a function f of x equals x squared. I'm told my interval is from 0 to 2. So I have to tell you that f is differentiable from 0 to 2, and it is differentiable because it is a polynomial. F is continuous, mistake already. That needs to be an open interval. And it is continuous from 0 to 2. And then I need to find the slope. So I need to find the slope from 0 to 2. And therefore, by write everything out here rather than just saying it. So by MVT, there must be some place f prime of c that's equal to f of 2 minus f of 0 over 2 minus 0. Okay, so I'm going to go find those values. You can stop the video right now and try to solve those yourself. So based on what I just did here, again, I needed to find the slope between the 2 points, and I found the slope between the 2 points. I know that the derivative must equal the slope, so here is the derivative. It must equal the slope, which I found to be 2. I went over here and I found the derivative, and I set the derivative equal to 2, and I get x equals 1. And I always want to double check that it's in the interval. So there are 5 more questions that are pretty fast. Why don't you try those 5 questions, and I'm going to finish them on the next page. So again, I'm just going to start with the first one I have here, which happens to be x squared minus 5x plus 8. Let's set that up as f of x equals, just to keep it consistent, minus 5x plus 8. My interval, I am told, is from 1 to 5. And I need to start with my statements that f of x is continuous over the closed interval. F of x is differentiable, and again, it is continuous, and it is differentiable because it is a polynomial. So by MVT, there must be some place where f prime of c is equal to f of 5 minus f of 1 over 5 minus 1, and I'm going to go find those parts and pieces. You might want to stop the video right now and start working on this. So again, I went ahead. I found by MVT, my derivative must equal the slope, and so I set my derivative equal to the slope between those 2 points, and I got 3, and I always double check that it's in between the intervals here. I'm going to go ahead and I'm going to work on the other problems. Again, stop the video and start working on those other problems. They're pretty straightforward and pretty easy. So I worked two more of the problems, the one with sine and the one with x cubed. And again, notice all of the steps that I'm taking here to show my information. I did use my calculator to graph or to solve for the cosine of x equals 2 over pi. And again, I have to show you that I'm throwing out an extraneous answer here. Same thing down at the bottom with x cubed. When I'm solving this, technically it's plus or minus the square root of 7/3. And I have to make sure that I show you that I'm throwing out the negative, because a negative is not in the interval. But we have a couple of more questions. I'm going to work on those two just to give us a little bit more of the practice of just writing up what MVT is. So again, finishing the last two questions there, you'll notice I highlighted that subtraction sign just to make sure that we find that and carry that through. And again, it's continuous, it's differentiable, therefore by MVT, there must be some place where the derivative is equal to the slope of the secant. And so I found the slope of the secant, I got negative 1/4. And I found the derivative, and the derivative of 5 minus square root of x is that negative 1/2 over, or excuse me, negative 1 over 2 square root of x, and that has to equal negative 1/4. And again, by cross multiplying, I solve for x equals 4. Second one, 2x plus 1, I notice that this is a line, and the slope is always 2 on a line. And so I know that a line is continuous and it is differentiable. Therefore, by MVT, is there any place between there? There must be a place, at least one place between there, where the slope of the secant is equal to the derivative of the function. And the slope of the secant ended up being 2. And the derivative is 2. And my question is, when is 2 equal to 2? And it's always equal to 2 from 1 to 7, because again, it is a line. Alrighty, so let's try a couple of questions that are going to be a little bit harder. Same thing, make sure that there is a statement about continuity, about differentiability, and then go on and find that C value. You might want to stop the video right now, because I'm going to stop and start working on this, and then see if your values agree with mine. So again, it is continuous, it is differentiable. So continuous, it is differentiable. And by MVT, so again, continuous, it's differentiable. By MVT, the derivative must equal the slope. I plugged in 9. I plugged in 2 as my endpoints, and I got 3 minus 2 over 9 minus 2, and I got 1/7. I found my derivative, and I just rewrote my derivative so that I have a positive power. And then by cross multiplying, I get 7/3 equals x minus 1 to the 2/3 power. And looking at this, again, when I have this 2/3 power there, so I have that 2/3 power. In order to undo a power, I take and I raise each side by the reciprocal of that power, and that's why I raised both sides to the 3/2 power. So again, that's a 3/2 power that I raised it to, and then I had to take that negative 1 and move it to the other side, and I got 4.5642, which is between 2 and 9. Here's another one. Try this one. So again, I multiplied that x all the way through because that derivative would be easier. I do have to make my statements that it is continuous. You're going to get bored with that. It is differentiable, and then I have to tell you that I'm using MVT. So let's see. And by MVT, the slope of the secant must equal the slope at some point, or number of points. So I found the slope of the secant, which I got to be negative 1. The derivative I found to be 3x squared minus 2x minus 2. I set those two things equal to each other, and then I used factoring to solve. Remember that you have to set it equal to 0. Okay, that's a lot of you are making that mistake when you are trying to factor this. Anyway, so I got negative 1/3 and 1 as my answers, but 1 cannot be an answer because I can't have an endpoint as my answer. It must be between the interval by MVT. Okay, so this is another way of looking at MVT. And I am asking myself, suppose that f of 3 is 5, f prime has to be less than or equal to 4, and I'm using MVT to determine what is the upper bound for f of 8, or what is the highest y value for f of 8. So again, let's take a look at the work I did. I'm telling you it's continuous, it's differentiable, because I need to do that in order to talk about MVT. And I set up my relationship, which is the slope of the secant must equal the slope between the two endpoints. And my endpoints are going from 3 to 8. And so I set up that relationship. And actually, part of the relationship I know is I'm asking is there a possibility for f prime to be less than or equal to 4? And so I said f prime must be, and so again, I set that relationship. I just had to stop and do a little thinking there. And excuse me, using my cross multiplication, I ended up with 25 as the upper boundary for f of 8. So try the same thing with f of 0. You'll notice in this case, let's switch colors here, if I'm using f of 0 and what I know about f of 3 here, that I'm talking about the closed interval from 0 to 3. So stop the video and try setting that one up. So again, I'm going to make some statements about continuity and about differentiability. So I'm going to tell you it's continuous, it's differentiable. Sorry, I need to add in there. So by MVT, because I have to tell you what the heck I'm using. So by MVT, I set up such that the slope of the secant is equal to the slope of the derivative, or derivative value. And my derivative value, again, is what I'm given at the very beginning, which was that it must be less than or equal to 4. And so I set up my variable, or my relationship here. I plug in 5 for f of 3. I don't know f of 0, but I do know that when I subtract my x's, I get 3. I do a little cross multiplying, and then I'm going to subtract that 5, and I get a 7. Notice I have a negative sign there, so when I divide both sides by -1, I have to flip my inequality, and I get a -7. And then my statement is that f of 0 must be greater than or equal to -7. Same type of question. These have appeared on common exams. That's why we're looking at them. So start out, make your statements about MVT. Set up the equation for MVT and see if you can solve this. So stop the video right now and start with that. So I basically repeated what I did in the previous question. I have to make my statements about continuity, about differentiability, and then tell you that I'm going to go ahead and use MVT. I always set up MVT and start working that. It's hard sometimes to realize what this statement is. Notice that the direction of the inequality, and I have to use that same direction of the inequality, whereas this is the f of x value, and f of x is always less than or equal to, so when I plug that 5 in, 5 has to be greater than or equal to the slope of that secant. And when I solve, I get f of x must be less than or equal to 17. So that's the upward bound of 17, or of 4. So again, this was an AP question from a while ago. So let's take a look at this. See if you can answer that question. I'm just going to kind of noodle through it right here. So again, I talked about the fact that it is a continuous function, but it is not differentiable, and is not differentiable because we have a corner right there. So MVT does not apply, but I still can find the average rate of change, which is -2/7. Even if it was not, even though it's not differentiable, that doesn't necessarily mean there isn't a point at which the slope of the secant would be equal to the slope of the derivative. MVT just guarantees that that happens. If this function is twice differentiable, that means it is a differentiable. It is considered a continuous function because it would, if it was discontinuous, it would not be differentiable. Continuity does not guarantee differentiability, but if it is differentiable, it must be continuous. And so by MVT, I can use MVT, and I set up the slope of the secant equal to the derivative value. I solve for the slope of the secant, which is -1, and by MVT, I'm guaranteed that there is at least one place over that interval of 2 to 5 such that there must be a derivative value that's equal to -1. Alrighty. So last question, this is the stereotypical question about MVT, and let's read through this one. So the first thing I know for sure is that this function is continuous, so oopsie, sorry about that. This function is continuous and differentiable, and it is continuous and differentiable because he can't teleport. And I just have to figure out my endpoints. So I am starting, my endpoint is going to be 0 to 8 minutes. The problem here is that I'm talking in miles per hour, so I can't use 8 minutes. So I either have to change miles per hour to miles per minute, or I can change my 8 minutes to hours. And in this case, I personally would change my 8 minutes into hours because I think in terms of miles per hour, not miles per minute. So I'm going to go ahead and do that. So again, I went ahead and switched my 8 minutes to part of an hour because I wanted to keep all my information in miles per hour. I noticed that the distance he travels is 9.7 miles. I know that it took him 8 minutes or 2/15 of an hour to do that. So I went ahead and I know that it is continuous over that closed interval. It is differentiable. Again, because he's not teleporting or anything. So therefore, by MVT, I know that there must be some place where the slope of the secant must be equal to the tangent line. And if I plug in that distance that he traveled, which is 9.7, over the time that he traveled, which is 2/15 of an hour, I get that he traveled 72.75 miles per hour at least one time in that trip. He might have gone over it. He certainly traveled under it, but I do know that at least one time he traveled over 72 miles an hour. Can I say that unconditionally that he was traveling too slow or that he was going less than 45 miles an hour, which you can also get ticketed for? And I can't say that because based on MVT, I only know what I know, which is it was somewhere between 55 and 55. So that's it. And see if you can finish the 4.2 problems.